Welcome, this is Professor Ridge and today's lesson 3.6, Absolute Value Functions. And our first learning objective for today will be graph an absolute value function. Understanding absolute value. Recall that in its basic form, f of x is equal to absolute value of x. Right? The absolute value function is one of our toolkit functions. So again, this is worth pointing out here. So this is one that we should become really familiar with. The absolute value is commonly thought as providing the distance the number is from 0 on the number line. So we think of it as distance. So if we had a number line, and let's say here's 0, and you wanted to know the absolute value of x, so let's say here was x, the absolute value of x is going to be that distance. Right? So if this is at -5, the distance x is from 0 would be 5 units. So that would equal to 5. Okay, so it's kind of, another way we can think of it, about it algebraically is for whatever the input value is. So if you put in -5 here, the output value, the output is the value without regard to sign. So if I'm over here at +5, and let's say this was x again, all right, then that distance, the absolute value of 5, the absolute value of +5 would just be 5. So in both cases, they're 5 units from 0, right? So that's the idea. And again, so if we can think of absolute value in this context geometrically, right, it's the distance from 0, then we can think of it algebraically as a split function, right, a piecewise function. So there's two cases. If x is a positive number, if this is over here at +5, you're just going to leave x alone. So just stay 5. But if x is less than 0, so if x is -5, you're going to take the opposite of -5, which would be 5. Okay, so if we do absolute value of -5, that's this situation, so that's going to be the opposite of whatever x is. X is -5, which is 5. Okay, so this is the way we think of it as a piecewise defined function. So algebraically, we can define absolute value this way. Example 1, using absolute value to determine resistance. Electronic parts, such as resistors and capacitors, come with specified values of their operating parameters, resistance, capacitance, etc. However, due to imprecision in manufacturing, the actual values of these parameters vary somewhat from piece to piece, even when they're supposed to be the same. The best that manufacturers can do is try to guarantee that variations will stay within a specified range, often plus or minus 1%, plus or minus 5%, or plus or minus 10%. That'd be pretty imprecise, that one. Suppose we have a resistor rated at 680 ohms plus or minus 5%. Use the absolute value function to express the range of possible values of the actual resistance. Okay, so our first thing is figure out what is 5% of 680. So 680 times 5%. 5% is 0.05. Right, remember you move it 2 decimal places. So if it's here, 2 decimal places, take away the percent sign, in case you forgot. Times 0.05 equals 34. So that's 34 ohms. Okay. So again, if we think about the geometry, 680 is going to be right here, and we want to be within 30, or absolute value is going to be within 34 units. So we can figure out the minimum and the maximum. That's not what this is asking for. They just want us to write it as an absolute value function. So the absolute value of our resistance, we'll use R for resistance, minus 680. So the difference between R and 680 has to be less than or equal to 34 ohms. Okay, that's pretty much all you have to do for this one. Now if you wanted to solve it, you just subtract 34 to get the lower end and add 34 to get the upper end. Alright, graphing an absolute value function. The most significant feature of the absolute value graph is the corner point, also known as the vertex, at which the graph changes direction. This point is at the origin. Okay, so this is our toolkit absolute value function that we should know. So if you do these points, absolute value 0, 0, absolute value of 1 is 1, absolute value of 2 is 2, and then negative 1, absolute value of negative 1 is 1, and then an absolute value of negative 2 is 2. You plot those points, you get this V. So this should become super familiar to you that you can graph it no problem. Okay, and again, this is actually corner point. Let's use some more math lingo here. That's the vertex, right? That's the bottom of the V. And once we know our toolkit function, the basic one, from what we learned in the last section, all our transformations, you can graph basically any absolute value function. So you could do a vertical horizontal shift. It's also, if the more math term would be translation, which is the same thing as a shift. We can do the vertical stretching and compressing. So we make this V skinnier or fatter. I don't think any of these are compressed. So they're all vertically stretched. Right? So 2, that's a vertical stretch of 2. So we're going to take each y coordinate, multiply it by a factor of 2, and it'll make it skinnier. And then the minus 3 inside on the x is the horizontal shift to plus 3. Remember, if it's on the inside, it moves it, it does the opposite effect. So for this one, so let's see. Actually, what they did, there's the 3 transformations. That's what they're showing here. So they're going to start with the vertical shift of shift it to the right 3. So that's the red dotted one. Then we do the vertical stretch of 2. So that's the green one. So here it's at 1. 1 times the y value. Look at the y value. 1 times 2 is 2. And then here on the red one, it's 1, 2. You're going to take the y value times it by 2. So 1, 2. It's up here. Okay? And then you do that for all the points. Or what I do is just do 1 point on each side just to get the V. And then you're going to shift it up 4 units. So just take this green V that's skinnier and move it up 4. Okay? So that's using the transformations that we learned in last section. Example 2, writing an equation for an absolute value function given a graph. Write an equation for the function graphed in figure 4. So what we have to do is first figure out what the transformations are. So if we start with our basic toolkit function, well, let me leave it like this. So if we have y is equal to absolute value of x, zero, 0, 1, 1, 2, 2. You don't have to, you can probably just do 0, 1 and negative 1. That's fine. Or 0, 2 and negative 2. I'm going to go ahead and do these 5. Typically I do like 0, 2 and negative 2. Absolute value of negative 2 is 2. So this is going to be 0, 0. Let's use a different color just to kind of So let's do red 0, 0, 1, 1, 2, 2, negative 1, 1, negative 2. We get our V. Let's use a dotted line. Okay, so that's our original toolkit function for absolute value. Oops. So now let's describe what's happening. To get from here to here, this vertex to this vertex, it looks like we have to go 3 units to the right and down 2 units. So we're going to shift 2 units, or no, 3 units, sorry, 3 units down, and oh, I'm sorry. I don't know where my head is. Okay. 3 units right and 2 units down. All right. So, and then look at the V. It's skinnier. So if you pretended this way, I think of it. If this was the origin, if it's the red dotted one, here's 1, 1, but then do you see how this is going up to 2? And then here's 2, 2, but you see how that goes up to 4? So for our basic one, 1, 1 is getting, so again, if I pretend this is origin, 0, 0, this point would be 1, 2 instead of 1, 1. Okay? So that means I'm doing a vertical stretch by a factor of 2. Okay? So then now I'm ready to write my equation, and if you remember the way we're going to do this, so y is equal to the vertical stretch is the factor, the factor in front, and then if I want to move 3 units to the right, I do minus 3 in with the x. And if I want to do down 2, I'm going to do minus 2. And that's it. Okay, so our basic form is going to be a x minus h plus k. The k is our vertical shift. The h is our horizontal shift. And remember, you change the sign. So if it's minus 3, it's going to go right 3. And the a is the vertical compress or stretch depending on the value of a. And then if it's negative, it flips it upside down. Right? So those are all the things we learned in the last section, and we can apply it to the absolute value function. You can apply it to any function. And our last learning objective is solve an absolute value equation. This is a nice short section compared to the last one. All right, let's get to it. Solving an absolute value equation, solutions to absolute value equations. For real numbers a and b, an equation of the form absolute value a equals b, with b being greater than or equal to 0, will have solutions when a equals b or a equals negative b. Now if b is less than 0, then the equation absolute value of a equals b has no solution. I like to kind of point this out, this last one here. If you think of it again, no matter what you do, no matter what number a is, so let's say b is negative 3. No matter what number I choose for a, this is going to have no solution, because if I put a negative number in here, the absolute value of a negative number is going to be a positive number. If I put 0, in here, the absolute value of 0 is 0. So remember, a solution to an equation is what makes this statement a true statement. So when is a positive number equal to a negative number? And the answer is never. When is 0 equal to a negative number? And again, it's never. So this will have no solutions. So you can just stop, and if you get this situation, absolute value, doesn't matter what's inside, If it's equal to a negative number, there's no way that can ever be true. So the solution set's going to be empty, or you can say there's no solution. Okay. Now, if this is a positive number, then you have the two cases. So if I had, say, for instance, absolute value of A is 7, well, if I put in -7, absolute value of -7 is equal to 7, that's true. Or if I put in +7, absolute value of 7 is equal to 7. So this number in here could be equal to -7, or this number in here could be equal to +7. So that's how we attack these problems. So if this is a positive number, we translate this into the statement down here, this compound statement. Okay, if it's 0, A is equal to -0, which is just 0, or A is equal to 0, which again is just 0. So if this is 0, we'll just have the one answer. Right? How to, given the formula for an absolute value function, find the horizontal intercepts of its graph. So you're going to isolate the absolute value term, so get the absolute value part all by itself, and then use the idea that if the absolute value of A is equal to B, then you're going to convert it to this compound statement, A is equal to B, or -A is equal to B, assuming B is greater than or equal to 0. You know what? I don't like doing it that way. I actually like to put the negative on the B side. So this way I'm going to do it, even though the book, if you multiply both sides by -1, you get A is equal to -B. Because I like to think of it as what I was saying in here. This number inside could be -7 or +7, right? So what they're doing is they're putting the negative over here. They're saying that this could be 7 or, right? So you could do it, and you can see these give you the equivalent answer, right? Same thing here. So you can do it either way. I prefer the way that I had the logic in my head. I like to do it this way. Okay? So this is the statement I'm going to write, even though this book emphasizes it that way. Hopefully that doesn't cause too much trouble for you. You could do it either way. All right. So our first step is we want to find the zeros of an absolute value function. So the zeros of a function is when the function value is equal to 0. So this is the function value, the formula. So we're going to substitute this absolute value of 4x plus 1 minus 7 in for the f of x and solve it for x. Those x values are what we call the zeros of the function. So you just take the function and set it equal to 0 and then solve it for x. Okay, it's an absolute value equation now. We want to get the absolute value part all by itself. So we're going to add 7 to both sides, or remember the shortcut, you can just move it, change the sign if you don't want to show the step. Now from here we got the absolute value all by itself equal to 7. So again, I'm going to do it my way here. I'm going to say the number inside this thing, this expression inside, if it's equal to 7, the absolute value of 7 equals 7, which would be true. And so the order doesn't matter which way you do it. So you can do the +1 and then the -1, or vice versa. So that number inside could be 7, or that number inside could be -7. That's the way I like to do it. Okay, so the book is saying you put the negative, the book is saying you're going to put the negative on this side instead of that side. And you'll get the exact same answer as long as you don't make any mistakes solving that. All right, so again, I'm going to do it this way. Again, for the way that the logic works in my head, I like this way better. Okay, subtract. Now we're going to solve each of these statements separately. So we get 6, divide by 4, and then reduce it if you can. So divide both those by 2, we get 3/2. Now we're going to do the second statement in this compound statement. 4x is -8, divide by 4, x equals -2. So our solution set is 3/2, comma, -2. And you can check, if you put in -2, we get -8 plus 1. Plus 1 minus 7. So -8 plus 1 is -7. And then the absolute value of -7 is 7. 7 minus 7 is 0. So that one checks. So if I do the 3/2, so we're checking this. So this should be, we want it to be 0. So 4 times 3 is 12, divided by 2 is 6, plus 1 is 7. Absolute value of 7 is 7. And then that one works. Okay, so both of them work. Okay? And you're not required to do this. It's just good habit to check when you're doing, to make sure you didn't make any mistakes. Okay, and that brings us to the end of this lesson. So that was a nice short one. Hopefully it makes sense. And again, practice, practice, practice. I'll see you next time.